This video is about a really fast-growing function. If Ripley's Believe It or Not had a mathematics edition, statements in this video would definitely make the cut. To describe the sequence, let's take a number, say 21. Let's write it in hereditary base 2. That means that you write it in base 2, and then recursively write even the exponents in base 2. Now we change all the 2's to 3's, and we get a number that's larger than 7 trillion. Change all the 3's to 4's, and you get a number with over 150 digits. Then 4's to 5's, and it'll keep on growing. It'll continue to grow forever if we go on like this. It's growing pretty fast, but it's absolutely nothing compared to even the function f3 from the previous episode. This sequence wouldn't make it to Believe It or Not. To get it there, we have to make it grow a little more slowly. How does that work? Well, let's see. Let's start over, except this time we subtract 1 every time we increase the base. So we start at 21, change 2's to 3's and subtract 1. Again, it becomes larger than 7 trillion. Before moving to the next step, we need to make it hereditary base 3 again. Again, we go to around 10 to the 150. Notice that here, subtracting 1 makes the number's hereditary notation look very different. And it proceeds like before. Which is reasonable, all we did was subtract 1 now and then. However, these subtractions play a major role. Believe it or not, this sequence doesn't even keep growing. It eventually reaches 0. Let's see more examples, but with more manageable numbers. Here's the same sequence, but starting with 1. At the second term of the sequence, it reaches 0. If you start with 2, the sequence is 2, then 1, then 0. It reaches 0 at the fourth term. Feel free to pause and go through these examples yourself if you want to feel more comfortable with them. With 3, it reaches 0 at the sixth term. With 4, it increases a bit faster, and it doesn't seem to be slowing down. It still ought to reach 0, and I'll tell you at what step it does reach 0. Believe it or not, it reaches 0 at the nth term, where n has over 100 million digits. And I know I'm saying believe it or not, and you are free to not believe it. But this is actually true. These statements are true statements. Let's do one more believe it or not, going back to the sequence we had starting at 21. That sequence reaches 0 at the nth term, where n is so large that it dwarfs the outputs of the programs we saw in the last episode of the BIGNUM BAKEOFF series. How does one prove these claims? I'll try to give you a proof by example in this video. It can be made into a formal proof. Welcome back to the BIGNUM BAKEOFF series. If you've not watched the previous episode, you want to. I will be using concepts from it in the explanation. What we saw in the introduction was the definition of the Goodstein function, g. G of 1 is 2, because if you start at 1, you reach 0 at the second term of the sequence. G of 2 is 4, G of 3 is 6. And here we have my favorite complete the sequence question. What comes after 2, 4, and 6? 100 million digit number, of course. Now you're not going to try verifying this claim by actually computing the sequence. How do we do it then? This is one of those cases where we have two different mathematical processes that might look very different, but are in fact very similar. Computing a Goodstein sequence is actually very similar to computing functions in the fast-growing hierarchy. Let's start with the number being 3 to the 2 and the base being 3. To make the bases clear, let's keep track of the base separately and replace all 3's with the letter b. You won't ever come across this specific scenario when trying to compute g of k, but we're trying to understand the Goodstein operations, so this is still worth it analyzing. Let's start with the subtract 1 operation. Subtracting 1 would have been easy if we had a 3 to the 0 term, because then we just remove it. Since we don't have such a term, we'll start by simplifying 3 to the 2 as 3 to the 1 times 3. This isn't base 3 now, but if you would be so kind as to indulge me for a bit, I'll bring it back to base 3 soon. There still isn't a 3 to the 0 term, so let's simplify a 3 to the 1 term to 3 to the 0 times 3. Now there is a 3 to the 0 term, and if we remove one of them, we will be back to base 3. But before we remove it, let's see another computation. Let's compute f2 of 3. By definition as given in the previous video, this is f1 of f1 of f1 of 3. And f1 of 3 is f0 of f0 of f0 of 3. In the computation on top, things appeared thrice because the base was 3. At the bottom, things appeared thrice because the constant was 3. And you can see that the top and bottom are strikingly similar. Every term on top is mirrored by a similar term at the bottom, with the number of b to the 2's, b to the 1's, and b to the 0's being the same as f2's, f1's, and f0's. That was the simplification phase. Now we actually do the operations. On top, we subtract 1 and increase the base, removing 1b to the 0 and changing the base from 3 to 4. At the bottom, we compute the innermost f0, thus replacing f0 of 3 with 4. The similarity still survives, and we can continue these operations until we can't subtract anymore. Now we have to simplify. When we simplify b to the 1, we're replacing it with 6b to the 0's because the base is 6. And when we compute f1 to the 6, it is replaced with 6 f0's. They're both doing the same things still. The equivalence is between the exponents of b on top and the functions below. Let's fast forward now to the end of the Goodstein sequence. We reach a b to the 0 with base 23 on top and f0 of 23 below. On top, we subtract 1, we get 0, and we stop without increasing the base. At the bottom, we compute f0 of 23, and we get 24. This happens only on the last step, because the stopping condition is different. So if we want to know what base the Goodstein sequence stops at, we can just compute f and subtract 1 from the answer. We didn't see what happens if the original term had a b to the b. Say we start at 3 to the 3 at base 3. When we try to simplify it, we have to decrease the exponent, so we change it from b to the b to b to the 3, and then simplify as before. On the bottom, this corresponds to f omega. F omega of 3 does by definition simplify to f3 of 3. Any b's in the exponent above become omegas in the functions below. Before we proceed, here's another example if there's some confusion. Believing this proof by example, we can proceed to compute g of k. G of k is the length of the sequence starting at k. The sequence starts at base 2, so the length of the sequence is the final base minus 1. So along with our previous observation, g of k is the same as the value of f minus 2. The steps to compute g of k are as follows. Write k in hereditary base 2 notation. Change the 2's to 3's. We have to do this manually because our previous calculations were for subtracting 1 and then increasing the base, whereas the Goodstein sequence starts off with increasing the base from 2 to 3 before subtracting 1. From this point onwards, it is as shown in our proof. We compute the appropriate f's with the input 3, and then we subtract 2 from the final answer. Now let's use this to prove our claims. The first, believe it or not, said that each sequence reaches 0. We can actually compute when it reaches 0. So it definitely does reach 0. The second, believe it or not, was about the length of the sequence starting at 4. 4 is 2 to the 2, so that is b to the b. So g of 4 would be f omega of 3 minus 2. I've shown the computation if you want to check it. I'm using the fact shown in the previous video that f2 of x is x times 2 to the x. The final, believe it or not, was about the length of the sequence starting at 21. Being larger than the output of the programs in the previous episode. Let's recap the largest output. It was Pete7.c, which output f omega to the omega of n, where n is a power tower of 2's of length 36. Now 21 is 2 to the 2 to the 2 plus 2 to the 2 plus 2 to the 0. So g of 21 would be f omega to the omega of f0 of 3 minus 2. f0 of 3 is 4, f omega of 4 is f4 of 4. f4 corresponds to repeatedly power towering, so this would be much larger than a power tower of length 36. So this Goodstein function grows faster than f omega to the omega. Where exactly does it lie in the fast-growing hierarchy then? We can see that as we increase the input size a bit, the behavior of the function changes drastically, so we can't actually put it anywhere in the fast-growing hierarchy yet. It transcends any tower of omegas. There is a limit ordinal defined as the limit of the tower of omegas, and this is what the Goodstein function acts like. So it's similar to f epsilon naught. One of the contestants of the BIGNUM BAKEOFF did notice this and use it for his entry. Marxin.c does the Goodstein operations, and then, since there was more space, codes some other simpler functions and combines them all. David Moews analyzed the code and gave the upper bound shown here for the value Marxin.c returns. Marxin himself had a comment saying that if you're not using a similar function, you're not even going to be comparable to his entry. A pretty confident comment. That's pretty bang on. Well, it would have been pretty bang on had there not been that one contestant who decided to use a power of programs that transcends repetition. But that's for a later video. A beautiful channel, PBS Infinite series, has a couple of relevant videos. One is related to the Goodstein sequence itself, with extra details that I haven't given here. It mentions how omega, or a concept of infinity, is necessary to prove that the Goodstein sequence reaches 0, despite the definition of a Goodstein sequence having nothing to do with infinity. The other is related to the mathematical hydra, a beast that is also intricately linked to our discussions here. There's also a megafave numbers entry that uses g of 4 and mentions some details I decided to skip. I'll link to that in the description. Goodbye for now, and have a great day.